All right, very good morning to all of you. I'll begin today's session. Today's session will be on single phase fully controlled converter supplying a RL load. Now the components or the contents that we had covered so far, they include the power devices, and then we had come across power electronic converters. In that, the first power converter that we came across was AC-DC controlled rectifier. Now, within an AC-DC controlled rectifier, we had the option of looking at a half-wave controlled converter, which used one SCR. And when an inductance was present, the inductor stored energy. As a result, current was flowing through the SCR even when the supply voltage had reversed its polarity. Therefore, some sort of a negative portion or a tailing portion was available in the output voltage waveform. Whereas in case of a pure resistive load, nothing such an observation, because no such observation, because the phase, I mean the phase difference between an voltage and current will be zero, or in other words, current and voltage will be in phase in a pure resistive load. Therefore, whenever the voltage came down to zero, current also would come down to zero in case of a pure resistive load. And then we extended the conduction for two half cycles, in which the first converter that we came across was single phase half controlled converter. There were two ways of arranging two SCRs and two diodes. One is we can have the SCRs in one leg, or we can have the SCRs in one section. So one is called a symmetrical configuration. The other one, wherein legs contain the devices, that is called as asymmetrical configuration. However, the operating principle for both the configurations will be exactly same. Because there were four devices used in a single phase bridge, the number of half cycles that would be rectified will be two, or in other words, both the half cycles of input voltage would be rectified. However, because only two out of four devices are controlled devices, we call this as half controlled rectifier or half controlled AC-DC power converter. Now, in a half controlled power converter, which is also known as a semi-converter, though an inductance was used in the load, there will be self-freewheeling action, because of which the output voltage will never go to zero. Always the output voltage will be positive. And current, they are flowing through SCRs and diodes. SCRs and diodes are unidirectional devices. Therefore, current will always be positive through the load, through the supply. Supply will be in AC form, whereas through the load, it will be always in DC form. Therefore, the quadrant of operation, if you take the VI quadrant of operation, single phase semi-converter will give you positive voltage and positive current. This is what we had seen so far. We will take up single phase full bridge converter in this session, in which you will find that both quadrants of operation, or in other words, two quadrants of operation, positive voltage, positive current, negative voltage and positive current, both are going to be possible. Now, you need to understand that the current through the load will always be only in one direction. It cannot reverse, because we are using unidirectional devices, be it SCR or diodes. All are unidirectional devices. Therefore, current through the device, hence current through the load, will flow only in one direction, which will be from, you can assume, top to bottom, or through the load, it will be in only one direction. Whereas voltage polarity can reverse in a fully controlled converter. We will see how it happens. I'll start sharing my screen. I'll take up the circuit, and then I'll explain the operating principle. Now, try to recollect that we are now using four SCRs. Whereas in a semi-converter or in a half-controlled converter, two were diodes. Because all the devices are controlled devices, this is called as a fully controlled converter or a full converter. Now, the special feature of this full converter lies in the operating quadrants. Now, the full converter can give positive voltage, positive current, which was given or which was yielded by the semi-converter as well. In addition to this first quadrant of operation, the fourth quadrant, where voltage becomes negative, whereas current is going to be positive. So that quadrant of operation is also possible in case of a full converter. So you call this as minus V plus I operation. whereas the first quadrant is plus V plus I operation. This is quite obvious. Now, this is the advantage of a full converter. It can operate in two quadrants, minus V plus I. This is the special feature. Now, how do we get minus I? We will discuss. First of all, we'll take a plus V plus I. That will be a classical way of understanding. And from there, we can actually extend the operation to the fourth quadrant. We will see how it is possible. We consider a sinusoidal voltage source. V is equal to Vm sin omega t. And as usual, we start understanding the operation from omega t equal to 0. At omega t equal to 0, two devices, T1 and T2 would be forward biased, but they are not receiving a gate pulse till omega t equal to alpha. Therefore, till omega t equal to alpha, T1 and T2 will remain in forward blocking state. At omega t equal to alpha, when they receive a gate pulse, they start conducting. When the devices T1 and T2 start conducting, then current starts flowing from the supply through T1. Then it flows through the load from top to bottom. Top terminal therefore acquires a positive voltage polarity because supply voltage is positive. You can understand from the waveform of the supply voltage. Therefore, top terminal will be positive. Then current flows to the bottom terminal through T2. The circuit closes. As a result, the load voltage will be same as the source voltage. Hence, if you try to draw the load voltage profile from 0 to alpha, the devices are not conducting. We may have to redraw this. We will do that in a little while from now. From 0 to alpha, no devices were conducting. Therefore, output voltage is 0. At omega t equal to alpha, the devices T1 and T2 start conducting. Therefore, V0 will be same as Vs. Now, this situation, V0 being same as Vs and the load being connected to the source will prevail as long as T1 and T2 are conducting. Now, at omega t equal to pi, the supply voltage reverses its polarity. Therefore, T1 and T2 will have the tendency to reverse their current, or in other words, current through them is going to be brought down to 0. However, this is where the load inductance comes into play. Because of stored energy in the inductor and the electrical inertia involved, the current through T1 and T2 will continue to flow in the same direction. They won't reverse immediately because inductance has the property of opposing sudden change in current. So at omega t equal to pi, the supply is beginning to reverse its polarity. Therefore, current will also tend to reverse. It will tend to reverse, but then it doesn't allow, meaning the inductor doesn't allow. Therefore, current will continue to flow in the same direction. Therefore, the load voltage will also be same as the source voltage, even after the supply has reversed. Something what we observed in our one SCR based converter, half controlled converter. Therefore, from omega t equal to pi, depending on the value of inductance, depending on the firing angle, the conduction will continue to remain in the same polarity, but supply has reversed its polarity. Therefore, the same negative portion will be appearing across the load voltage. Now, at the instant pi plus alpha, the next pair of SCRs, T3 and T4 are triggered. Next pair of SCRs, T3 and T4 are triggered. You need to understand that at omega t equal to pi, the polarity of the supply would have reversed. Therefore, the bottom terminal of the supply would now be plus, top terminal would be minus. This is from omega t greater than pi, omega t greater than pi to 2 pi. I'm just writing it in a crude way. I hope you would understand. This is from pi to 2 pi. The polarity of supply voltage is marked over there. As a result, when the SCRs T3 and T4 receive a gate pulse at pi plus alpha, at omega t equal to pi plus alpha, they are already forward biased because of the supply voltage. Therefore, they will start conducting. Now, the moment T3 starts conducting, you need to understand T1 and T2 were conducting earlier, just before this instant. T1 and T2 were conducting. The moment T3 and T4 are triggered, they would start conducting. Now this is like, if you can imagine a relay race, one person handing over the baton to the next person. The next person will be waiting. Let's take 4 into 100-meter relay. There will be 4 people who have to run. Each person has to run 100 meters. First person starts with a baton in his hand, and then when he completes that 100 meter, the second person will actually grab that baton, and then he keeps running, passes on to the third person, so on and so forth. Exactly similar to that relay race. Here T1 transfers its current to T3. Similarly, T2 transfers its current to T4. Now, so T1 commutates, that's all. T2 commutates, gets commutated. T1 transfers its current and gets commutated. T2 transfers its current and gets turned off or commutated. That's all. Now we are not doing anything, meaning we are simply turning on T3 and T4 and we are switching off T1 and T2. Therefore, this process is called as natural commutation. The supply itself has that capability to turn off the SCR. Therefore, it is also called as natural commutation, the process of turning off, naturally commutated. All right, which means definitely there is one more category of converter which are going to be forced commutated converters. They are a different category. Let us not, we will discuss them later on, not in this session. So you need to understand this. The moment T3 and T4 are triggered, they start conducting. So current carried by T1 is transferred to T3, thereby T1 gets commutated. Current transferred by T2 will be, current carried by T2 will be transferred to T4, therefore it gets commutated T1. And what about reverse voltage? Look at the voltage across T1. See, you have a positive voltage appearing at this node, and because T3 is conducting, the cathode of T1 will be seeing minus voltage. Can you understand this? Minus voltage is appearing across the anode. Positive polarity is appearing across the cathode through T3. So voltage across T1 will be reversed. Similarly, T2 also will see a reverse voltage. Quite obviously, quite clearly, plus Vs will be appearing at cathode of T2. And minus Vs will be appearing at anode of T2 through T4 of T2. Therefore, T2 will also see a minus voltage, a reverse voltage. This is how T1 and T2 are commutated, because the supply naturally provides that reverse voltage and current is being transferred to the SCRs when they are triggered. This is called as natural commutation. These types of converters are called as naturally commutated converters. All right. So many points are there to be mentioned, to be understood. Fine. Then the same sequence of events from pi plus alpha till 2 pi. T3 and T4 will be conducting, load will be connected to the source through T3 and T4, load voltage will be same as the source voltage. Because load voltage polarity has reversed, source voltage polarity will be positive at the top, negative at the bottom. So it will be reverse of the supply voltage. And from 2 pi to 2 pi plus alpha, stored energy in the inductor will keep the devices T3 and T4 to conduct. Therefore, we will see a negative portion from 2 pi till 2 pi plus alpha. And at 2 pi plus alpha, quite obviously, the other pair of SCRs, T1 and T2 will be triggered, and then the conduction carries on like that, meaning the next cycle commences. So if you want to draw the waveform under steady state condition, this is, so this portion you can actually cut and put it over here. This is obviously because of the previous cycle. Or if you start from omega t equal to 0, if you miss out this portion also, you are correct. It's not wrong. It is correct. In MATLAB, if you try to simulate and check, you will see only 0 here. Thereafter, it will be continued. Okay? So this is the operating principle. Fine. Very quick recap of whatever we have seen so far. We are discussing continuous conduction mode of a fully controlled converter. From omega t equal to 0 to alpha, SCRs T1 and T2 will be forward biased, but they don't receive a gate pulse. Therefore, they won't conduct. They will be in forward blocking mode. At omega t equal to alpha, T1 and T2 are triggered. Therefore, current will start flowing from the supply through T1 to the load through T2, and then it gets back to the source. So load voltage will be same as the source voltage from from alpha to pi. Beyond pi, Due to stored energy in the inductor, T1 and T2 will continue to flow till omega T equal to pi plus alpha, wherein the next pair of SCRs, T3 and T4 are triggered. We are discussing CCM, continuous conduction mode. Our inductance is large enough. Now at omega T equal to pi plus alpha, T3 and T4 are triggered. Therefore, conduction starts and it goes on through T3 and T4. Load voltage will be same as source voltage. Again, stored energy in the inductance will keep the devices T3 and T4 to conduct just after 2 pi as well. At 2 pi plus alpha, next cycle commences. So this is what happens. Fine. Now, as I said earlier, this is continuous conduction mode. If you try to calculate the average output voltage for whatever waveform is shown over here, now V0 average will be given by 2 Vm by pi cos alpha. For this waveform, I'm not deriving, I'll just leave the derivation to you. So 2 Vm by pi cos alpha. This will be the expression for average output voltage. Obviously, alpha is the firing angle. Now, when alpha is made more than 90 degrees, what will be the polarity of V0 average? When alpha is more than 90 degrees, what can you tell about the polarity of V0 average?
Negative.
Negative. So this is the highlight of the full converter. How does that happen? And when will that happen? What are the conditions? We will discuss that. When load inductance, I make sure that it is very, very large. Okay. So load inductance L needs to be very, very large. I will indicate that as well because it is very, very important. Load inductance L is very high. Use a very large inductance. Now, when you keep advancing the firing angle to a state where firing angle is more than 90 degrees, then you will find that the conduction actually commences. Let's take, I have drawn the waveform for 120 degrees. So positive cycle will be for 60 degrees and remaining duration will be for the negative duration. Because I'm using a very large inductance, inductor will keep circulating the energy even though the source voltage polarity has reversed. Therefore, the polarity of output voltage will be such that the average voltage is going to be negative. I have indicated here. I hope you can see the pointer as well. V0 average will be negative. All right. Now, what about current through the devices, current through the load? They will still continue to flow only in the same direction as marked over here. Through T1, top terminal plus, bottom terminal minus. So current through the load will still be the same. As a result, V0 average polarity will be minus. But if you look at current, V0 average will be negative, but I0 is going to be positive always. The current cannot reverse its direction, quite obviously, because T1 and T, I mean, all the four SCRs, they are unidirectional devices. You can't force current from cathode to anode. Therefore, what will happen to power? If you look at power, product of both, power is going to be negative. Now, what does negative power mean? Minus P0 means, previous case P0 was positive. What did it mean? P0 actually absorbed the power. Now P0 is negative. What does it mean? Negative P0 means load is supplying. Load supplies the required power to the load, to the source. All right, load supplies, I will switch off and write it neatly so that you don't have any confusion. Switch off the camera rather. So P0 minus P0 means load supplies power to the source. Or in other words, power flows from the load to the source. Okay. So when power flows from the load to the source, so this is one thing. Power flows from the load to the source. All right, this is the other thing. So when power flows from the 1 minute, when power flows from the load to the source, it means we are actually reversing power. Positive would mean power flowed from supply to the load. Normal operation, AC-DC rectification. Whereas now, when alpha is more than 90 degrees, V naught is negative, P naught is negative. Therefore, power now flows from the DC side to the AC side. Now, how do we call this DC side to the AC side power flow? We call that as inversion motion. We call it as inverter, right? So DC to AC is actually inverter. So the fully controlled converter can operate as a rectifier, which is from alpha less than 90 degrees, 0 to 90 degrees. And it can operate in inversion mode as well, which is from alpha equal to 90 degrees to 180 degrees. This is the special feature of a fully controlled converter. Now, because power can flow in two directions, if you now try to plot the VI plane, I being positive, I being along the x-axis, V being along the y-axis, minus V over here. You can easily understand that plus V plus I is going to be possible. This is rectification, AC-DC conversion, whereas minus V plus I, this is also going to be possible. So this portion is inversion. Inversion, which means power flows from DC to AC side. Right? Now, DC to AC power, obviously, we call that as an inverter. Therefore, we call this power converter as, it is also called as a naturally commutated inverter. I will write that also incidentally, because I have opened it up, I will write it. It is also called as naturally commutated inverter. Sometimes it is also called as line commutated. Line commutated inverter. What does it mean? Load has large inductance, firing angle is more than 90 degrees. The converter operates in continuous conduction. Under these three conditions, the converter is going to operate as an inverter. We don't need any commutation circuit. Simple line is going to be enough to turn off the devices. Because power is going to flow from DC side to AC side, we call this as inverter. And the converter is termed as naturally commutated inverter. So this is the special feature of a naturally commutated inverter or a fully controlled converter. You need to understand this categorically. Now, so this is the summary of whatever we have seen so far. When alpha is more than 90 degrees, V naught becomes negative. Load voltage polarity reverses, devices are unidirectional, power reversal occurs, converter operates in inversion. Okay. It is also called as a phase controlled inverter. Phase control because we are adjusting the V naught value using firing angle technique, which is called as phase control. Now the conditions are load L must be high, converter must operate in continuous conduction mode CCM, alpha should be more than 90 degrees. The gist of inversion mode of operation. Of course, this is the classical power flow. Power flow from AC side to DC side. This is the reversal power flow from the DC side to the AC side, V naught being negative, polarity of V naught being negative. I have marked it this way because the average magnitude of V naught will be negative. Therefore, I have reversed its polarity. What happens when you have a beta? Beta, we had assumed that beta was equal to pi plus alpha, or rather beta was less than, therefore that was CCM. Now, beta greater than. This is a case where beta is less than pi plus alpha, meaning load inductance is small enough. If you don't have sufficiently large inductance, only a very small value of L is there, or rather reasonably big value, but not big enough for CCM to be maintained, then you get into discontinuous conduction, which means conduction stops at a particular value of angle beta. Beta, you should recollect, is called as extinction angle, the point where the current through the load becomes zero. This is called as extinction angle beta. Classical way of naming, classical terminology, extinction angle. Alpha is firing angle, beta is extinction angle, conduction angle will be sigma. This is how the waveform should be. So the stored energy in the inductance would have expanded at omega t equal to beta, and SCRs T3 and T4 won't receive a gate pulse. They receive the gate pulse only at pi plus alpha. Therefore, conduction cannot happen from beta till pi plus alpha. Therefore, load voltage will be zero. This is what happens till omega, or from omega t equal to beta till pi plus alpha. Fine. Now, this is again for you to understand. Specifications, I have just simulated RL load for two conditions. One is R load under 500 watts, RL load under 500 watts at 0.8 power factor for two firing angles. Let's see the simulation results. This is for alpha equal to 30 degrees. Of course, this is for RL load. For R load, it will be similar to our semi-converter. So R load, I have not included here, included the simulation results here. 30 degrees CCM, continuous conduction mode. You will see that this is what I was mentioning. First portion in simulation will not be there. Under steady state, yes. So whatever we have seen, whatever we had discussed, ideally under CCM happens. This will be alpha, this will be pi plus alpha, 2 pi plus alpha, so on and so forth. Continuous conduction. Okay. So when alpha is made 45 degrees, again the same thing. This is again CCM, no differences at all. For this is for 500 watts, load at 0.8 power factor, lagging. Now, I had made the inductance very large, and then I had captured the input current waveform and the output current waveform. So the input current is going to look like, you can modify this, or when you use an even larger value of alpha, these small undulations would be ironed out, which means the input current is going to look like a square wave. You can even now assume, or not even assume, model this input current to be a square wave. The modification or the modeling is going to be fair enough. The analysis would still be fair enough. Fine. Whereas the output current will still be an envelope. And if you can observe closely, look at the 0 point. 0 point is somewhere here. Right? And the output current stays well above 0 throughout the operation. I'll draw the 0 axis so that it becomes clearer to you. Now, 0 axis or x-axis of the output current is going to be somewhere here. Right. So it stays well above 0 throughout its operation. Therefore, it is perfectly CCM. And obviously, large inductance is used. Now, I was referring to this point. So you can still model this to be a square wave. The analysis would still be perfect. Now, the inference is, if you use a large inductance input current waveform, I in will be a square wave. Please understand this. Square wave for large L value. When you get a question, what will be the shape of input current for large inductance value? The answer is square wave. Now, what is the input form? Input form is going to be in AC form, input current. Input side itself is AC side. Now look at this. Voltage is sine wave, but current is square wave. Fine. Now, when you get a square wave, you should recollect the concept that you had come across in. I had taught myself in your network theory. When you have a square wave, it introduces harmonics. So this is the problem of rectifiers, controlled rectifiers. Voltage will be sine wave, but when you use a large inductance, then current becomes a square wave. It automatically changes its shape. Nobody does nothing. Therefore, that will introduce current harmonics into the AC side. In the AC side, that creates problem for the other devices that are connected in the same AC side. So this is one of the power quality issues. I will write it as PP, power quality issues. Nobody does nothing deliberately. See, the user simply inserts a rectifier and then uses a, let's say, motor load which is going to have a large armature inductance. Then he finds that the input current has turned to be a square wave, and that introduces harmonics. So it is, the user can claim that it is not his problem, but no, he can't shed off his responsibility. It is his equipment that is generating all these harmonics. Therefore, it leads to a lot of power quality issues. Okay. So that those things you need to understand. You can discuss them later on, or if you are interested, you can simulate them, find out what is the harmonics, you can find out what is the power factor as well, what are the ill effects of harmonics, things like that. That's a different study altogether. But for your understanding, till this you must understand, you need to understand this. Voltage is sine wave, but when inductance is large enough, input current becomes a square wave, harmonics are introduced, power factor falls down. These are the problems. So very good. I have denoted them or made a note of them as well. Supply power factor will be poorer than a semi-converter because of that self-revealing mode. Semi-converter will offer a better power factor. And the applications are regenerative braking of DC drives, grid-connected PV systems. These are, I told you, they are very important practically. So this is the importance. They are used in regenerative braking of DC drive and grid-connected PV system, which means if you have a PV panel, you put a rectifier, operate that as an inverter, then power automatically flows from the PV panel to the load. So the schematic would be, now this is going to be in DC form. I will write it as VDC. And then somebody can put a single phase, I will write it as single phase fully controlled converter. And for indication, I will write it as alpha greater than 90 degrees. Then I will connect this to a grid. There will be control other things. All those things are going to be there implicit. Now, because alpha is more than 90 degrees, power is going to flow from the DC side to the AC side. This will be the direction of power flow. Okay. So this is the schematic of a grid connected PV system. One of the arrangements, one arrangement. Other arrangement is going to be DC, you invert and then you have control. That is another simpler way. That is what people are using. While majority of people, they are actually using DC-DC converter followed by the inverter arrangement because that gives them flexibility to control. But very simple way, if you don't want any complications with regard to sine wave and other things, this is also possible. So that's all about a single phase fully controlled converter. I think it's over. Yes.